Hello, everyone. Welcome to another URISA webinar. My name is Matt Garricky, Professional Education Committee Chair for URISA. URISA is a multidisciplinary geospatial organization that provides professional education and training to support geospatial professionals at all stages of their careers with essential training and resources. One of the things we've heard over the last several years from URISA members and the GIS community is, well, can you find someone to talk about machine learning? How can I use machine learning? How exactly is machine learning different from all this other stuff that we do as GIS folks? And after hearing these questions for several years, we're very happy to have a presentation today. Capabilities, considerations, and case studies, demystifying the use of machine learning in the geospatial world, which seems to really put the round hole, or the round peg in the round hole of what many geospatial professionals have been asking for and seeking about this topic. And so we are quite pleased to have three presenters from Dewberry, Catherine Bohn, Paul Dean, and Sid Pandy, talking to us about this topic. So looking forward to a great and interactive presentation. Just the one matter of housekeeping. We do have the chat function turned on. We also have the Q&A function turned on. And so if you want to chat, please use chat. If you have a question that you'd like to ask, that you'd like the presenters to come back to, or you think might be answered over the course of their presentation, please put it in the Q&A section. It helps us manage a little bit easier on the back end the flow of questions, and I'm sure we'll have lots of interesting and exciting questions come up from today's talk. So Catherine, I'll turn it over to you and your team. Thank you.
Thanks, Matt. Thanks, Matt and Wendy, for organizing this session. We're really excited to be here today and talk about machine learning. And thanks to all the participants on the call for taking time out of your schedule to attend this session. So like Matt said, we're here to talk to you today about demystifying machine learning in the geospatial world. Together with Paul Dean and Sid Pandy, we'll talk through the capabilities of machine learning, discuss some of the factors and considerations that you should think about when developing a machine learning process, and give you specific examples of case studies. So today we're going to do something a little bit different. We're going to use something called Menti to give you a way to collaborate with us in this presentation. We really want you to share your ideas. You're going to use your phone or tablet or secondary device and go to menti.com and enter the code. You're going to want to make sure to have these slides up on a second screen so you can see what's going on, and then use your second device to enter in information. We really want to hear your ideas. We want you to participate because we can all learn from each other on this. And of course, most importantly, please keep your comments professional. All right, so let's go ahead and get everybody a little bit of time to log into Menti. So you can go to menti.com on the second screen and enter in the code 4667-9591, or you can take your phone and scan the QR code to log in to Menti that way. And I'm seeing a lot of hearts down at the lower right-hand corner. So that's the number of people that have gotten into Menti and are able to access these slides. So I'm going to give it a couple more seconds till the heart flow seems to die down a little bit. One thing that we've noticed with Menti before is, for some reason you don't feel like contributing to a specific question that we have, Menti will let you know that you need to then get to the current slide. That way you can continue to follow along on the slides. All right, so it's looking like it's about where we need to be. So let's move on and let's test out using Menti. So if you could all let us know, where are you joining us from? What location are you in? And so as we see the words are coming in, we've got people from across the country joining us today. This is so much fun. And so people joining from the same location will start to see the words get bigger as more and more people say that they're joining from the same location. So we've got a lot of people, it looks like, from Los Angeles, Pittsburgh, California, Texas, Virginia Beach. Give us a second to take a look at all of these different locations. Oregon. We're actually joining you today from Fairfax, Virginia. Both Paul, Sid, and myself are all from Fairfax, Virginia. So hopefully that gave you a little bit of a taste of what Menti is like, and you had fun using that audience response session. In the introduction, we're going to do a couple more slides like that to get a better understanding of what it is that you want to learn about in relation to machine learning. Then Paul's going to spend some time going over some common definitions of machine learning and terms associated with it, and then talk about a process that you can use to implement your own machine learning. In order to get you thinking about how you might use machine learning, Sid's going to talk about specific use cases and give 3 examples. And then, like Matt mentioned, we'll leave some time at the end to start talking about the questions. All right, here's another Menti question. When you think about machine learning, what word comes to mind? I like that first word that popped up, intimidating. And that's really what we're here today, is to help it be less intimidating. And automation, I think that's one of the key things, is how can you take a process that is typically very labor intensive, very manual, and automate it to expedite your workflow. Terminator is a pretty good one as well. And like I mentioned at the beginning of this presentation, we'll be sure to share these slides with URISA so that everyone can get, all of this input and we all can learn from each other. So lots of great terms on here, and a lot of terms that Paul is going to cover in his session, and a lot of ways of how we'll show machine learning being done during Sid's talk on the use cases. We've got one more question for you on the introduction piece, is what are you hoping to get out of this session? And this will be a little bit different than the word clouds. You'll be able to enter in what you want to get out of the session, and we should start to see that scroll on the screen. And we definitely hope you walk away with a better understanding of machine learning, at a minimum understanding some concepts. Hopefully you walk away excited with the capabilities of machine learning and being able to use certain use cases. I see one question that I know Paul will address, is how AI is different than ML. That's a great one. And you can see now we're starting to get a lot of different inputs, and so they're scrolling through. We will talk about the process of machine learning, how to apply it. I think it's important to understand specific case studies and real-world applications, all in part to help demystify the use of machine learning. I like the input. Is this something I can really use without a new degree? Yes, it is. We've got three use cases that we're going to show you, and a lot of those use cases are applicable for local governments. And each of the use cases that we're going to show you today have a geospatial focus around them. And I do see one item when we don't have a list of resources in this presentation, but it's definitely something we can share on resources where you can quickly learn more about machine learning for free. Okay, great. Like I said, we'll share all of these great inputs with everybody after this presentation. But now I want to go ahead and turn it over to Paul to talk about machine learning terms and processes. So Paul, over to you.
Thanks, Catherine. Good afternoon, everyone, or morning, given the how far apart some of us are. Thanks for taking the time to join us this afternoon. I'm going to, over the next several slides, talk through some fairly basic terminology surrounding AI, machine learning, and deep learning, and some of the practical applications in the geospatial arena. If you do have any questions or want any clarifications or anything, please, again, do use the Q&A, and we'll take it from there. But getting started here on this particular slide, we see the three terms: artificial intelligence, machine learning, and deep learning. And you'll notice that this visual seems to imply that each is a subset of the other. And so one way to kind of organize these terms is to think about artificial intelligence as any way of leveraging a computer's power to think to start to solve problems. So the term AI can cover a whole host of different subject matter, tools, processes, what have you. It's pretty broad. So as we drill down from there and we get into machine learning, what we're really kind of talking about is starting to leverage specific algorithms to take an input, interpret it in some way, and then provide some sort of output. So a real easy way to kind of think about that is like if anybody uses Pandora or Spotify, if you listen to 4 Rick Astley songs in a row, there's a high probability the next one is going to be Never Gonna Give You Up, right? Because that model has taken your inputs and recognized some trends in your selections, but also compared to the trends of others. So, Spotify or Pandora, they're not using that simple algorithm of just an artist name. They're incorporating all other sorts of factors like genre or year published or tempo or other users that have similar listening patterns to you and what else they're listening to. So there's all these sorts of other parameters that are being factored in. And so that recommendation gets a little bit better over time. So that's one way to think about machine learning. Now, as we drill down into deep learning, we're really starting to talk about attempts to get these kinds of algorithms to mimic the cognitive abilities of humans. And these are typically or frequently done through the use of neural networks. Now, the neural network is basically taking a series of black boxes or little cognitive inputs or filters, and they take an input and they interpret it and give some sort of output based on some sort of previous training. Now, the intent is not to necessarily mimic the mechanics or the physiology of the human mind, but more the ability to take in disparate kinds of data or stimulus and make sense of it. So where, machine learning in general may be solving a relatively simple problem like what song should I listen to next, deep learning is really starting to drill down into, is this a picture of a cat or a picture of a sandwich? So there's a lot more considerations to make in there, sometimes down to the pixel level and sometimes based on some other sorts of contextual information. So we can go to the next slide. Thanks. All right, so as we're talking about machine learning and pretty much for the rest of this presentation, leaning on deep learning, There's a couple different ways to further subdivide. So one way to that academia and industry subdivides machine learning and deep learning is into supervised learning, unsupervised learning, and reinforcement learning. So supervised learning is essentially taking a process where you provide labeled training data. So the input, along with an explanation of what the intended output is, you provide that to a model, it in turn learns that. And then when exposed to similar inputs in the future, it should be able to predict the output. So you're supervising the learning of that model by providing inputs. And in many instances, the quality of your training data or labels, as you can see in that little visual above, data plus labels into ML model leads to trained ML model. The quality of those labels or training data have a direct impact on the ultimate performance of the model. So we'll talk a little bit more about that in a subsequent slide. But the key there is you have an understanding of the inputs and a clear understanding of what you want as an output in a supervised learning situation. Now, when we talk about unsupervised learning, we're not providing any training data to the model at all. We're expecting it to figure it out on its own, unsupervised. And so the way you can apply these models is a little bit different. Whereas you may train a model to identify pictures of cats on the internet. With unsupervised learning, you may say, here are all of the pictures on the internet. How many of each are there? Or how can we organize them? Are there patterns? Is there any kind of clustering or density based on location? So this is really taking large volumes of data and trying to make sense of it rather than make a, some sort of determination. And so that second visual there where you see input with all of the little visuals unorganized, and then the model applied to that data could create some sort of groupings that provide some sort of insight to researchers or industry. And then finally, reinforcement learning is an approach where you use a model to optimize some series of activities or processes so that a model can iterate on the proposed processes or options or alternatives and try to get closer and closer to whatever win or success conditions and criteria exist. So the goal is to have the model figure out how to do something the best. So one way of conceptualizing this is if there's a lot of videos on the internet of, academia or, in some instances, even high schoolers developing reinforcement models that can optimize the completion of a level on Super Mario Brothers, for example. The computer knows exactly which button to press at what time to get to the end state in as quick a time as possible, maximizing points. So that would be an example of reinforcement learning. Next slide. Thanks. Okay, so those were some kind of high-level discussions of terminology or subdividing machine learning and deep learning. So how would one apply this in the real world? So this and the next couple slides are going to talk through a kind of process or workflow to get it a desired end state. So you generally want to implement machine learning when you have some sort of problem you want to solve. It's easiest to come with a problem rather than lead with a tool in search of a problem. And so the kinds of problems you want to solve with machine learning are, they need to be of a sufficient magnitude for it to make sense. So if you have a column of 100 instances of a piece of data and you want to put them in alphabetical order, this is not the time to use a machine learning model. If you have 100,000 instances of point features in a particular geography, and you want to organize them in some way or make some sort of inference about those point features based on, you know, whatever underlying data there is, that's where you may want to use some machine learning. So you don't always necessarily need to limit your conception of business problems to just making things you already do easier or automating tasks. You can also start to think about machine learning as a way to tackle problems that were previously unattainable or unachievable for, you know, humans or a team of humans to do in any kind of reasonable time frame. So regardless of how you pursue that, you do want to define a workflow as you move through the steps of machine learning, and structure that so that you can be prepared to both interpret and reproduce your results. Because as you may find in any kind of internet research, machine learning sometimes turns into a black box where you provide some inputs and say, the computer figured it out, and here's the answer, without any kind of real understanding. And that can be dangerous. So we can move on to the next slide, please. Okay, so drilling down into the front end of the process. Once you have your business problem, you want to start to try to identify the best tool to address that. And earlier I had talked about supervised learning or unsupervised learning or reinforcement learning. In many instances, supervised learning is what we're going to be applying in the geospatial arena. And you can even subdivide supervised learning a little more into terms like image classification or object detection or instance segmentation or image segmentation. And these are all trying to achieve slightly different things. So image classification is basically if you had a series of images, specific discrete images that had some sort of information on them, and you wanted to train a model to identify other images and associate those with, you know, a particular category, so that you already know specifically where the input is. So that's going to be image classification. Then there's object detection, which is where you may have a huge image or aerial imagery, and you're trying to detect particular types of objects in that imagery. So that's a slightly different.
Right, folks.
I'm back. Can you hear me?
All right. Yes, we can hear you now.
Strange.
Yeah, sorry, I'll go ahead and share my screen again, everyone.
Okay.
Can everyone see the screen okay?
Yep.
Okay, great.
Okay. Thanks. So what was I rambling on about? So as you identify a particular machine learning model to apply to solve some of your problems, you're going to want to figure out how to implement that. In the geospatial arena, there's a handful of tools that make it relatively straightforward to dip your toes in the water. So most of the most popular or prominent geospatial applications software have some commercial off-the-shelf, baked in machine learning workflows that are worth exploring. We're going to talk a little bit about one of those in the use cases later on, but whether or not that workflow is baked into the software, there's also open source plugins if you're an open source person. So without too much trouble Googling, you can find a lot of those tools. And so once you conceive of not just the model and how you're going to implement it, you need to get a sense of the scope and scale of the challenge you're trying to address. Because in some instances, if it's a relatively straightforward machine learning process you're implementing, you could run it locally on a laptop with no issue. But as you scale up to assessing huge volumes of aerial imagery, for example, you're probably going to want to lean on some sort of scalable cloud architecture to use only the resources you need. In some instances, it makes sense to invest in the hardware yourself and have that kind of processing power on premises. It really varies on the use case, but it does vary, and it's worth considering before getting real far down a path. We can move on to the next slide. Thanks. Okay, so this particular part of the process is specific to supervised learning, where you're going to want to establish some sort of training data so that your model has been exposed to enough types of cases that it's adequately equipped to provide the outputs you expect. And this can be an extremely time-intensive process. Depending on the particular problem you're trying to solve, there may be open source training data available that you can pull down or reference on the internet. Alternatively, you can develop training data yourself by identifying inputs and interpreting them or labeling them appropriately. And then there are public and private sector organizations that do generate training data. You provide them the raw materials and a concept of operations, and then they'll pull that together. Regardless, it can take a considerable amount of time to generate enough training data so that it sufficiently represents what it is you're trying to do. For example, if one were to assess lawn types in residential areas, that imagery on the East Coast is going to look considerably different to those kinds of lawns on the West Coast or in the Midwest. So you want to make sure if you're assessing those things that you have training data to cover the various parameters that may show up. We can move on to the next slide. Okay, so you've put a model together, you've got some training data, you fed it in, your model's trained, you have some data you'd like to test to evaluate the performance of the model. This is all good. But as you get your first results, you may find that they do not align with what you had anticipated. And so you may need to start to evaluate the architecture of your model. And this is where, it can get a little complicated. A lot of the elements of a machine learning model you can tweak are called hyperparameters. And that doesn't sound like, relatively straightforward vanilla, geospatial work. It's fairly sophisticated. So as you start to tweak those things, you'll probably need to lean on documentation associated with whatever software you're using. And you'll want to make sure that as you tune these parameters that you're getting performance from both an accuracy but also a speed perspective, because sometimes one hyperparameter can cause a model to run over a series of days rather than minutes and achieve essentially the same outputs. But once you do get those outputs, sometimes that's good enough, and you've got a model, it functions to some reasonable, achievable, acceptable level of accuracy, and you're done, and you can move forward from there. But depending on your use case, you may want to take those outputs and validate them and correct them, and essentially add to your training data library so that you can feed that back into a model to improve its accuracy in the future. And so on the next slide, we we show a general workflow that we use in a lot of our disaster recovery work. So you can see it starts in the upper left-hand corner with the event. So some event occurs, and then some imagery is acquired related to that event. We receive and pre-process that imagery, and then we apply a machine learning model to it. And we obtain outputs. We review those and get them to a sufficient level of accuracy and completeness, and we deliver them to whoever our end user is. But then we take those corrected outputs and we retrain. And so we're constantly improving the model. And this kind of cyclical process is useful in a lot of instances, but may not be warranted for your use case. So that's sort of a quick overview of AI, machine learning, and deep learning. I'm sure there's some questions in the chat that I'll try to take a look at. But as we move on from here, I think Sid's going to talk about some interesting practical applications and use cases for machine learning. Thanks.
All right, thanks, Paul. Hopefully you all got a good kind of baseline understanding of machine learning. I noticed some folks at the beginning said, or were asking questions like, is this something I can do? And where can I start? So hopefully you're starting to feel a little bit more confident that this is something that you're able to do. And hopefully by the end of this section, you'll have a lot more confidence in knowing exactly where you can start applying machine learning within your own organization. Next slide. All right, so we're just going to go through 3 use cases that we're seeing. I think just in the geospatial community alone, we're just scratching the surface with how machine learning can be used. One of the more prominent examples we've been noticing is in the emergency management, emergency response arena, so conducting damage assessments. What you're seeing on the screen here, the image on the right is an output from a machine learning model that was classifying residential damages to these structures and classifying them based on different degrees of damage. So that's created using a classification model, and depending on where you live and the types of natural events you might experience, whether that's hurricanes, significant rain events, tornadoes, wildfires, the kind of damage you might see at a particular structure could be very different than in other locations. And so you can create various types of classification models that can be used to detect different types of damages, whether that's roofs being torn off or fire damage or blue tarps on a roof and things of that nature. And so you can really create custom models for your geography or the type of damage, or even the type of buildings or structures that you're working with, because there's a pretty significant amount of differences in those cases. And as Paul was describing, the model allows you to kind of churn through all this information relatively quickly with all of the inputs that you've provided, and it will give you an output. And that output can sometimes be good enough to be used or taken forward to your end user or your stakeholders. But in some cases, it might require some review. And I know a lot of times when people think about machine learning, they think like, oh, well, if we teach computers how to do this, like we're basically just working ourselves out of a job. And that's not necessarily the case. There's a lot of importance behind having the human in the loop in this whole process. On the left-hand side, you're seeing an example of an image that was assessed by a machine learning model, and it gave an initial classification based on the way it was trained that this structure has sustained a certain amount of damage. The human eye can then, with all the other context clues that it has, can then validate that response and say, yes, it's accurate, or no, it's not, and they can raise or lower the damage value. That then allows you to provide a more accurate response to whoever your end user is, or the decision maker that might have to make important decisions very quickly. But that also allows you to then improve your model, because that just gives you more training data you can put back into the system. And so it's really nice that you can churn through a lot of this information, get yourself to a good point very quickly, and then use the kind of the human eye and all of the background information and context that we have to improve that and improve your model as well. And then of course you can report performance of the model as well, so you can see how it's doing and of course improve it over time. Next slide. Another example I'm sure many of you are familiar with is using machine learning with building outlines. So in the geospatial community, having good building footprints is one of the most prized data sets you can have. And a lot of times these are collected in a very manual way. You might have folks who are digitizing them, or they're extracting them from imagery in certain ways. And so using a machine learning model, and there are many out-of-the-box solutions, some free, some not, that you can leverage, you can detect these building outlines and create these data sets for yourself. And in many cases, if you already have this kind of information, you can update it so that you're always current as well. What you're seeing on the screen in this image, the red polygons were building footprints that were collected with older imagery. In this case, I believe it was oblique. So you're noticing that some of those outlines aren't aligned correctly with the buildings in this image. And in the yellow, that was new development that was developed in that area and also was detected using a machine learning model with the latest imagery. So you can obviously see that over time you can start to correct your building footprints with new and more accurate imagery. You can update old footprints as well as collect new information as well. So you're always staying current. You can detect change as well too. So if folks are getting additions to their homes or structures are being demolished or modified in some way, it can detect that and update your data set as well. Next slide. And then the last example I'll quickly walk through here is in the remote sensing space. So if you're familiar with either of these images on the left-hand side here, it's basically a digital elevation model with shown in a hillshade as well as a LiDAR intensity. So producing a high quality elevation model, requires you to assess and categorize all of the LiDAR points that we would then derive an elevation model from. And in some cases, especially in an area where there's a large bodies of water, that LiDAR doesn't penetrate all the way to the surface as well as it could on land. And so you have to hydro enforce those particular areas and enforce a static elevation. That's manually done, by collecting what are called break lines, or essentially boundaries around these water bodies, and then it's essentially everything inside that boundary has one static elevation enforced. As you can imagine, that's a fairly time-intensive and manual process. However, using LiDAR intensity imagery and various other inputs of information, you can train a model to detect where that line is between land and where the water body would begin. And based on other parameters that you provide it, you can essentially delineate all of these break line or water body boundaries, and then extract those and run your hydro enforcement process. And this is just one application in the LiDAR space. I'm sure many of you are doing a lot of things with remotely sensed data. And so, we just want you to walk away from this knowing that machine learning is a good way to churn through a massive data set like an elevation model or a raw LiDAR point cloud and be able to delineate or detect and even extract certain features from the data. Next slide. Okay, so I think we've reached the end of our presentation. Again, we really hope that you've taken away some good information about what machine learning is and maybe how you can use it, and have seen some use cases of where it's currently being used in the geospatial industry. But before we kind of jump into the Q&A and questions, we'd really like to hear from all of you one more time and just see if any of you out there are currently using machine learning, or if you're thinking about it, what are some of those use cases for you? And hopefully someone else on the call who might be doing something similar might be inspired by what you're saying. So just a good opportunity for us all to share potential use cases. Forest health monitoring. Okay, yeah, habitat classification, self-driving, object detection, interesting. Okay, I was actually just talking to somebody earlier today about using machine learning in the utility space. Okay. Very interesting use cases. As you can see, there's a lot of really great ideas here. I'm sure some of you are already working on some of these, and some of you are probably thinking about how to get started. Again, hopefully you have a little bit better understanding of machine learning and how you can get started. Catherine, I think we can move to the next slide. Got some great ideas here. So with that, just on behalf of Catherine, Paul, and I just want to thank URISA for this opportunity to present, and to everyone who called in today just for your time and for your feedback and your thoughts in this interactive presentation. And at this point, we're happy to take any questions, and we've left our contact information on the screen as well. So if you'd like to talk more about any of these or ask us any follow-up questions, we're happy to connect with you.
All right. Thank you, Catherine and Paul and Sid for giving us some context and language and examples to help us get our heads around what's meant by folks talking about machine learning today. One of the questions that's come up a few times in chat is, so what's really new about this? You know, it seems like some of these things, some of these examples you've talked about, you know, folks in the remote sensing space have done for quite a while. And so David asks, do you consider object-based image processing to be a form of machine learning? Do you have any guidance or insight on how we can kind of think about what GIS folks have done previously and how that's being, is that being captured? Is that being rebranded? Or are we just thinking about it differently? You know, if we're talking about machine learning and artificial intelligence and that sort of thing.
I'll take a stab at that one, and then Paul and Catherine, if you want to chime in. I wouldn't necessarily say it's a rebranding. I think that there's just kind of, you know, there's new technologies. The models might be becoming more accessible to folks, and I think the barrier to you know, to entry or being able to do this kind of work is getting lower, just with this geospatial community providing, you know, so much of the way they're doing their work as openly as they are. Yeah, I would say, you know, what's done in the past could still be considered machine learning, but I guess with new technology out there, maybe it's changing a little bit.
Paul or Catherine, any thoughts on that question?
Yeah, I think Sid answered it well, and you know, I'm just getting to all the great questions that are in here. So I think we probably can go ahead and move on to the next question.
All right. Are you aware of any ways that folks have applied this to look at social equity in terms of affordable housing?
Yeah, it's interesting. We actually took a look at how damage assessments after disasters are related to social equity. So yeah, there are definitely examples out there in the industry, and you know, using all the different, you know, geospatial data layers to then put into this model could definitely help answer those questions. Paul, I don't know if you want to elaborate any more from some of your research.
Sure. I guess a minor addition to that, you know, using machine learning to assess damage to structures relies on, you know, a picture of the structure itself. The model doesn't understand or care what is damage related to a disaster or a storm or something versus what is, dilapidated or not unmaintained structure. And so it's helpful to ensure that we're ground truthing whatever outputs we're getting from machine learning models relative to social vulnerability indicators in those particular geographies. I don't know if I articulated that well enough, but trying to minimize any kind of bias on when conducting damage assessments across large geographies.
So it's kind of, if we're pointing an algorithm at something, it's only looking at what we're pointing it to. And just because we're using an algorithm to try to pull out one thing doesn't mean that correlation, and it's that correlation causation thing, right?
Yeah.
And so it may pull out something that identifies something or pulls something out based on that algorithm, but that doesn't mean that actual event or disaster caused that thing to appear that way. I'm not sure if I help clarify that in any way, shape, or form, but I think that's where you may be going with that.
Yeah.
All right. So Tom asked a really technical question, and so I'll refer you to it. It's the first one in the Q&A, and so it's asking, can you use imagery products with varying spatial resolutions within a single model? Are there any needs to downsample into a shared spatial resolution? Are there benefits to incorporating localized higher resolution imagery products in machine learning analysis?
Yeah, and I guess I'll take a stab at this one. And we've definitely seen imagery of varying spatial resolutions being used for detecting and classifying information, and there are benefits to incorporating them all into a same model and using those higher resolution data sets to help detect those more nuanced pieces of information that you're trying to look at. For example, let's say you're trying to detect different roof types using a satellite or resolution imagery that may not be able to see certain things about the roof, whereas if you use those more localized higher resolution imagery, you could see it. So you could definitely incorporate multiple imagery data sets into one model.
Excellent, thank you. So I'm not sure I understand one of the other questions that we have in here. How is metaverse related? Any use cases? So I'm not sure if that's referring particularly to the thing that we used to call Facebook, or if there's another buzzword that we need to start adding on to our, we need someone to talk about this as it applies to GIS type folks. But any insight on that question?
Yeah, I'm not sure exactly either. I don't know, Paul or Sid, if you have any additional insight.
Yeah, I'm not sure there is a relation yet, but I guess I don't know enough about the metaverse to confidently say that.
All right. So one of the other questions that came in was wondering about if AI can be used or how it could be used in predictive models to anticipate natural disasters like flooding or wildfire.
Yeah, the prediction is an interesting idea, and there are models out there that can take a variety of different data sets, historical impacts, existing conditions about the geography that you're looking at, demographic data to understand the potential impacts, parcel information to run through to identify predicted impacts. We can talk offline about specific examples, but I don't know, Paul, if you have any additional input that you'd want to provide.
Not specifically. The topic's been discussed in academia, and there's several research papers available that are fascinating. To what degree they can be operationalized currently is a different consideration, but if you're interested in that topic, there is research available.
All right, excellent. So Tim Nolan asked a question, how could machine learning be used to capture spatial data in a large database? I'm not sure, Tim, I completely understand the question, so feel free to come off mute and elaborate. It seems like there's quite a bit of potential with turning other data sources into other data sources. Did you mean something particular by that?
Well, a lot of times there's, you just sort of have data. You hear this, I hear this all the time, 80% of all data is spatial. Well, let's prove it with machine learning, right? Let's turn, any data source that you have that may be unstructured, that's not clearly an address or coordinates or something like that. Can it glean or can it be trained to capture spatial data like a gazetteer or something, just a place name, anything like that, against huge databases, where you don't have staff to look through it? That's what I'm asking. Can it capture all that stuff?
Geocoding based on context rather than an address or something?
Kind of, yeah. Or just like, is there spatial data? Is there geographic data in this database? This collection of whatever it is I stumbled across. Can I, let the machine find it up for me?
I have not pursued that line of inquiry, so I'm not sure.
Okay. Thanks, Matt. Thanks, everybody.
Yeah. Thanks for the question, Tim. There are some tools that are out there that are, I think, becoming more apparent on that, but it's usually much more on the ones I've seen are more on the qualitative data analysis side, and how do you turn qualitative data or a bunch of text into location-based information. But we can chase down that rabbit trail at the next URISA event. We're both at, Tim. But that's a great thought-provoking question. Paul, early in your comments, you kind of mentioned that there's kind of a size threshold where if we're sorting 100 records alphabetically, machine learning would be overkill. But if we're dealing with 1 million points, that's well suited for it. And we have a question from Milton, kind of wondering about the minimal size of a data set. And I guess my reaction would be is it kind of depends on your purpose, on your question, what you're trying to solve. Do you have some examples of different kind of rough ballpark number of records, size of areas for some of the different scenarios that we've talked about where it might make sense to start going down the machine learning path rather than, alphabetizing in Excel or digitizing by hand?
I don't, but depending on how you're funded, I think performing some sort of ROI on machine learning and its potential benefits or optimization versus a more manual process is something that everybody should explore if you're pursuing any kind of material problem. But 8,000 things could be a lot of things or a few things depending on the nature of that thing. So, I don't know if there's an objective answer to that or one size fits all.
All right, excellent. So we have had a few questions come in about resources for learning more or staying current or training data sets or platforms. As you've worked to get your head wrapped around machine learning and started applying it in different areas, do you have any recommendations for how to keep up with what's going on and what may be some good resources to look at to follow up beyond today's webinar?
Yeah, there's a lot of resources that we've used that we'd be happy to share with after this call. And so Matt, I think that's for a follow-up discussion. I think there's probably a lot of resources that people on this call have that they'd like to share with everyone as well. So why don't we figure out a way to put those resources all in one central location for this community? Because I think it would be great for us all to learn from each other, and we will definitely provide the resources that we typically use as part of this presentation.
Excellent. I think that sounds like a great idea, and there's some folks contributing some items in the chat in response to previous questions. So that is, it's all about community. We're all passionate about geospatial technology and using it to help understand the world and solve problems. And so much of the learning can be done from each other. So would welcome that. So I think we've touched on all the questions that have come in. So once again, thank you, Sid and Paul and Catherine for your time and willingness to talk with us today. Before we wrap up, just wanted to let folks know about a few other upcoming URISA opportunities. Later this month, on March 18th, we'll be kicking off a series of 6 webinars from the 2021 Exemplary Systems in Government Award winners, some of which may have used machine learning, but you might have to attend all 6 over the next 6 months to find out what those might be. We will also continue to offer a live Q&A study session for those preparing to take the GISP exam this June. And we're also scheduling a virtual full-day GISP exam prep workshop, if that's something that's on your bucket list. Later on in July, we'll be offering one of our newer URISA workshops. A team put together a workshop on decrypting risk, resilience, and social vulnerability data and indicators workshop that debuted at GIS Pro in Baltimore last fall. They'll be offering that virtually in July, 2 afternoons in July, so spreading it out a full day, spread over 2 days. And so be on the lookout for opportunities about that. And if you like to see GIS people in real life and not just on camera, the GIS Valuation Technologies Conference is coming up later this month in New Orleans. And if you would like to share your own GIS passion, experience, expertise, please submit an abstract for GIS Pro. Deadline for that is March 15th, and that's for the meeting the first week of October in Boise, Idaho this year. If you'd like to explain what you're working on and give examples and help demystify and clarify things that you're passionate about for the GIS community based on your experience, and would be interested in doing a webinar or a podcast or writing a fact sheet or any number one of other mechanisms that URISA supports professional education, please reach out to us at the Professional Education Committee. Look us up on the URISA website, urisa.org, and reach out to us. We always have a long list of ideas that folks would like more training or different perspective on in terms of GIS. But we often find that some of the best presentations are by those that are passionate about what they're doing and how they're using it. And so once again, really thank Catherine and Paul and Sid for bringing their passion about machine learning to us this afternoon.
Thanks for having us.
Yeah, thanks.
Yeah, thanks everybody so much for your time. And I was just going through the chat, and happy Mardi Gras to everyone as well. So thank you again.